Good day everyone. Welcome to my channel Quick Tech Master Mariner. Don't forget to like, subscribe and press the bell icon to get notification of all other videos.
Okay, let's dive right into this. Welcome to today's explainer. Today we are tackling a massive topic, fractional distillation. We're going to demystify the complex and honestly fascinating world of crude oil.
So think about this for a second. Raw crude oil, straight out of the ground, is this tangled, messy mixture of hydrocarbons. How on earth does this single, thick, black liquid have the exact properties we need to fly a massive commercial jet at 30,000 feet, pave a super durable highway, and give us the clean-burning gas we use to cook dinner? It's kind of mind-blowing when you think about it. Well, the answer lies entirely in how we systematically heat and separate this raw material into its highly specialized parts.
To really get how this magic happens, we need to talk about our core concept for today, fractional distillation. At its heart, this is simply the process of taking a mixture and separating it out into its component parts, which we call fractions, using heat. The whole operation runs on one very basic fundamental rule of physics. Different substances trapped inside that crude oil mixture have different boiling points. By carefully controlling the temperature, we literally turn a chaotic, sludgy liquid into this beautifully organized, giant, heat-driven sorting machine.
When you look at the complete fractional distillation process, what's absolutely incredible is that you're essentially looking at an entire global supply chain mapped out inside one single structure. It's standing there like a giant metallic skyscraper right in the middle of a refinery. On one side, you've got the raw input and all this intense background plumbing, right? And on the other side, out comes the everyday stuff that literally keeps human society running. Everything from the fuel from massive cargo ships to the stuff inside tiny chemical flasks. It all originates right here, inside these stacked vertical chambers.
All right, so let's break down exactly how this giant thermal sorting machine actually works. It's basically a four-step physical flow. First off, the crude oil gets heated intensely in a furnace. Second, this superheated mixture, which is mostly vapor at this point, is pumped right into the very bottom of the towering column. Third, because heat naturally rises, those vapors start traveling up the tower. And as they get further and further away from that furnace at the bottom, the environment gradually cools down. Finally, step 4. As the vapors cool, different fractions hit their specific boiling points and condense back into liquids at very specific heights, where they're easily collected. So it's just this continuous, bottom-up journey of vaporization and condensation.
Let's zoom in on where this whole journey kicks off. Down at the very base of the system is the furnace, blazing with intense flames. Here, we're subjecting the raw crude oil to extreme temperatures, anywhere between 350 and 400 degrees Celsius. To put that into perspective, that is a massive, massive amount of energy just to jumpstart the process. We aren't just warming the oil up a bit, we are intensely boiling this thick, dense liquid until the vast majority of it flashes into a vaporous state, totally ready to begin its climb up the column.
But hey, not everything turns into a gas. As we start our climb at the very base of the tower, there's this thick, dark, sluggish material called residue that drops right out at the bottom. This fraction is made up of the absolute heaviest, most dense materials in the crude oil. Because their boiling points are so extreme, we're talking over 450 degrees Celsius, they just don't vaporize in the furnace. They stay liquid, drop straight to the bottom, and are gathered up for really heavy-duty applications. Remember that thick asphalt we need to pave those highways? Yep, that comes right from this sticky residue.
Now, if we move just one step up from that residue, we hit our first condensed fraction, heavy gas oil. As the rising vapors cool just a tiny bit, dropping to somewhere between 350 and 450 degrees Celsius, these really heavy molecules condense back into a liquid. This dense, powerful fuel is absolutely crucial. It provides the raw, immense energy needed to run the gigantic internal combustion engines of those massive cargo ships that are constantly crossing our global oceans.
Moving higher, we enter the densely packed middle section of the tower, which I like to think of as the ultimate transportation hub of the whole process. It's amazing how logically this flows as the temperature keeps dropping. Between 250 and 350 degrees, diesel condenses out, giving us the heavy-duty torque we need for freight trucks. Go a bit higher, cooling to between 150 and 250 degrees, and we get kerosene. That's the highly refined fuel commercial airplanes need to fly at high altitudes. And just above that, cooling down to between 40 and 150 degrees, we extract gasoline, or petrol, which is literally the lifeblood of our everyday cars and tractors. The tower is just perfectly sorting out our transportation fuels, layer by layer.
Continuing our climb past all those engine fuels, we reach a really fascinating layer called naphtha. This condenses in a relatively cool zone, between 70 and 100 degrees Celsius. Now, unlike the fractions below it, naphtha's primary destination is not an engine. It is actually a crucial feedstock for the petrochemical industry. Think plastics, synthetic fibers, and just a massive variety of industrial chemicals. It's solid proof that this distillation tower doesn't just fuel our world, it literally gives us the raw physical building blocks for the everyday stuff we use all the time.
And finally, we make it to the very top of the distillation column. Up here, the temperature is less than 40 degrees Celsius. The molecules that survive the journey all the way up to this point are the absolute lightest and most volatile in the entire crude oil mix. Actually, they're so light that they never even condense into a liquid inside the tower at all. This is liquefied petroleum gas, or LPG. It exits the very top as a gas and is later pressurized into those familiar, colorful cylinders, making it a perfect, easily transportable energy source for things like your home cooking stove.
When you compare these two extremes, it really builds a complete picture of just how incredibly efficient this tower is. Think about this stark contrast for a second. Up at the top, you've got LPG at under 40 degrees, light, invisible, volatile gases neatly packed away in pressurized cylinders. And out at the other bottom, you have residue at over 450 degrees, this super heavy, thick, sluggish sludge. This massive disparity really hits the nail on the head regarding our main point today. Thermal sorting is a ridiculously effective way to categorize vastly different substances from one single messy input, relying on absolutely nothing but the simple physics of boiling points.
Now, as comprehensive as this main tower is, the initial fractional distillation is really just step one. You'll also hear about secondary refining processes, things like catalytic cracking, hydrocracking, reforming, and delayed coking. Why do we need these? Well, the global market often demands way more of the lighter fuels like gasoline than raw crude naturally has to offer. So refineries take the heavier outputs and use these highly advanced secondary chemical processes to literally break apart or crack the heavier molecules into lighter, much more valuable ones. It's a real game changer for meeting our modern energy demands.
So we've just seen how a single tower uses heat to unpack the dense, ancient energy trapped in crude oil, transforming a sticky sludge into the very forces that drive our cars, pave our cities, and stock our store shelves. It's a total marvel of applied physics, and it operates largely out of sight, day in and day out. Which leaves us with a pretty fascinating final thought to chew on. What other invisible industrial thermal processes are quietly operating in the background, silently shaping the materials and the modern world around us every single day? Keep questioning, keep learning, and thanks so much for joining me for today's explainer.